Can a single, massively scaled, reusable spacecraft architecture actually establish a permanent human presence on another planet? SpaceX's Mars colonization plan outlines exactly how this could happen. However, it is a proposed future architecture, not a fully realized or currently capable mission profile. The destination is an average of 140 million miles away from Earth. Because of the distinct orbits of Earth and Mars around the Sun, launch windows to make this crossing only open roughly every 26 months. Once there, the surface conditions are highly lethal. The atmosphere is 100 times thinner than Earth's and composed of 96% carbon dioxide. It is characterized by extreme cold, persistent cosmic radiation, and pervasive, highly toxic dust. Operationally, the distance creates a communication latency of up to 44 minutes for a round-trip signal. If an emergency occurs, there is no chance of real-time rescue or troubleshooting from mission control. Mars is an actively hostile vacuum. It demands an unprecedented tonnage of survival infrastructure just to keep a small crew alive. To transport these massive payloads, SpaceX is building the fully integrated Super Heavy booster and Starship upper stage. The propulsion system relies on methalox, a propellant mix of subcooled liquid methane and liquid oxygen. The complex internal mechanics of the Raptor engines utilize a highly efficient full-flow staged combustion power cycle. This allows the full flow of both propellants through the turbines without dumping any unburnt fuel overboard. To survive atmospheric entry, the vehicle is defended by thousands of heat shield tiles that must withstand extreme thermal stress as they dissipate energy. The goal is rapid reusability. By catching the booster at the launch tower and executing the Starship landing flip, the architecture is designed to drive down the astronomical costs of deep space launches. While Starship theoretically solves the mass-to-orbit problem, reaching Mars requires it to first survive a highly complex, unproven sequential bottleneck in Earth orbit. A fully loaded Starship simply cannot escape Earth's gravity well with enough onboard propellant left to make the 140 million-mile trip to Mars. To solve this, the architecture relies on orbital refilling. Multiple tanker Starships must launch sequentially from Earth to transfer propellant to a waiting depot or passenger ship in low Earth orbit. This graphic, Starship HLS Prop Transfer Demo, illustrates a primary physics hurdle: cryogenic fluid management. In space, propellant is highly susceptible to boil-off. Transferring ultra-cold liquid methane and oxygen between vehicles in microgravity without losing fluid is a deeply complex mechanical operation. To keep the fuel stable during multi-month loiter periods, engineers must develop advanced cooling systems, utilizing multi-layer insulation and active cryocoolers. Without completely mastering deep space cryogenic fluid management and rapid-fire orbital rendezvous, the entire Mars architecture is permanently stranded in Earth orbit. During the months-long transit phase, the crew will face prolonged exposure to galactic cosmic radiation outside the protection of Earth's magnetic field. Arriving introduces the entry, descent, and landing paradox. Mars's atmosphere is too thin for heavy parachutes, but thick enough to generate mission-ending heat via friction. The solution is a precision landing using supersonic retropropulsion, firing engines directly through hypersonic airflow to slow the massive vehicle and touch down vertically. Because of these inherent risks, the first several Starships must be uncrewed, deploying robotic cargo, setting up surface power, and delivering life support habitats. These robotic precursors execute in-situ resource utilization. By mining Martian water ice and atmospheric carbon dioxide, they will attempt to synthesize the methane and oxygen needed for the return trip. NASA's MOXIE experiment on the Perseverance rover proved that extracting oxygen from Mars is chemically possible. However, there is a massive disparity in scale between a small rover experiment and an industrial propellant plant. Generating 1,200 metric tons of propellant on an alien surface is a mandatory industrial-scale mining operation that must succeed before humans can ever come home. While the physical rocket is actively being tested and improved, the surrounding surface and survival architecture remains largely theoretical. SpaceX must achieve flawless, rapid reuse, master orbital cryogenic refilling, and develop life support systems capable of running for years without maintenance. engineers must invent lightweight, effective radiation shielding and create seals that can withstand the highly abrasive, statically charged Martian dust. Finally, they must successfully launch a super heavy lift rocket off the unprepared, cratered terrain of Mars with zero launch pad infrastructure. Establishing a Mars presence requires a flawless, unbroken chain of distinct technologies, where a single failure at any step causes the entire architecture to collapse. It is a systems engineering mountain. Starship is the first vehicle in history with the physical scale to even attempt this chain of events, but the hardest parts of the journey have not yet begun.